Hello, I'm Nicholas Bergeron. I'm going to go over what I did for the Black Hole Lab, which is Lab 3 of our Physics 2211 class. The premise of the lab is that we have a black hole and a star. This is a planet, but it doesn't, the picture is a planet, but it doesn't matter. The same effect's going to happen because it's just mass. And we are given, we're given the mass of the star, as you can see right here, 2.0 times 10 to the 30 kilograms, and we are through our glow script when we type in our source code or our seed, sorry, we are given the position vector of our star as it orbits around the black hole, and using that we are going to calculate the mass of the black hole. So moving forward, here is an image of my glow script path. As we can see, here is our star planet, and here is our black hole. So we are finding, and the script actually gives us the position as it rotates around, or as it orbits around, and then using that, our script will give us the mass of the black hole. So let's say that we didn't have the script. Here is all the code that I use to calculate the mass of the black hole, which should say ki which should say kilograms right there for mass. Sorry about that. We would What we do is our code gives us fnet, fnet parallel, fnet perpendicular. So using the total fnet, we would rewrite our mass equation, and we would put it like this. So we would set mass of black hole equal to our new equation, and we would solve. We would use our fnet, our position vector, the gravitational constant, and the mass of the star. But for the code, our code was able to output it. So this is actually a very interesting path for our. I'll go back to this picture while I talk about the differences between fnet, just because it shows a path. So as we can see, and as we are given here, our fnet perpendicular is significantly greater than our fnet parallel, which makes sense because it's in elliptical shape. So as it gets closer, the perpendicular force is going to outweigh the parallel force. So if they were equal, it would be a nice circle, but it isn't because fnet perpendicular outweighs parallel. So it's going to move towards, well, it's going to change direction faster than it is moving forward. So it will not be a perfect circle just because of that. And the main differences, or how fnet and change of momentum are different, is because as our star gets closer or further away from the black hole, change of momentum does change. So as it's once it's right here and it's moving closer to the black hole, its rate or its change of momentum is going to be increasing just because it is getting closer. There's more gravitational force on our star, and I'll just assume that it's going in this direction. As it's moving past it, and then it moves out here, its change of momentum is going to start slowing down just because it is getting further away from the black hole. So the force of gravity is going to be significantly less. So let's say that the black hole whose mass we found was removed, and we were given a new black hole. So what would happen here? It depends on the mass of the black hole if the orbit would change. So if we have a new black hole that's added and this path is the same, the mass has to be the same because gravity, the only force acting on this is gravity. There is no air resistance. So if let's say I had a more massive black hole, it would have a tighter orbit as opposed to having a less massive black hole. It would be a looser orbit. Yeah, it would be a larger. Yeah. It would be a larger orbit just because gravity is the only thing that is affecting the orbit of the star around the black hole, because it's in space. It's a vacuum, and so yes, if we were to change our black hole and this path was the same, then for certainty, the mass of this black hole has to be the same. So yeah, that was my lab 3, the black hole lab. Thank you.